why don't we get started? And so where we left off last time, we talked about the characteristic shape associated with the probability governing or governed by the VC bound. And if we look at that expression, it had a polynomial. It was up in the uh, number of parameters, or in the VC bound, and we said that polynomial has a degree of d, where d is the VC bound. And then we had that negative decaying exponential. And that negative decaying exponential, well, it certainly had our error tolerance epsilon. It also had the dominating factor, which was that big N, which is the number of data samples. And so with this expression, this VC bound has a characteristic behavior where we have an increase when you have a small sample size n, and that increase is dominated by the polynomial term, which is the complexity of the hypothesis set. And as you get enough examples, enough in-sample points, n gets bigger, and then that decaying exponential starts to dominate the expression, and the result is that you end up getting eventually a very small probability on the right-hand side of the inequality for the VC bound. And so what this graph does, it depicts for different dimensionalities d, as d gets bigger in 5 increments of 5. So we have d equals 5 is the blue curve, d equals 10, 15, 20, and so forth. You see this characteristic shape where in the beginning, when you have a small number of in-sample points n, and n increases along the horizontal axis here, whereas on the vertical axis, we have the probability. Now, certainly it doesn't make sense for the probability to be greater than 1, but nonetheless, this is still the characteristic shape of what would govern the probability associated with the VC bound. And so we see as n is really small, of course, the polynomial, the complexity, is dominating, and we get an increase until eventually the decaying exponential takes over, and with enough samples of size n, we start to get very small probabilities, 10 to the minus 5, or even smaller. And so this is just to say that there is this relationship, this coupling, if you will, between the sample size, the model complexity, and the ability to get good coincidence, if you will, between in-sample error and out-of-sample error. And so there's a rule of thumb that says how many examples should you have on the order of 10 times the VC dimension as a minimum. Is it always a hard and fast rule? No, but it's a good rule of thumb to employ when you're building your models. Okay, so that's where we left off last time. Any questions about this? Okay. So let's take a look at the generalization bound, and we'll finish up the module with this slide. I think it's 1 or 3 slides, I believe. And so we began with the VC inequality, and we coined the following expression for the VC bound, which is the bound on the probability of bad things happening, and where that bad thing happening corresponds to the event where in-sample error diverges from out-of-sample error by more than some error tolerance or threshold epsilon. And so that probability is bounded from above by this VC bound, and that VC bound comes from the comparison of a hypothesis on 2n in-sample points, where you're taking 2 draws of size n of data, and you're comparing the relative performance between En and En prime. And so this quantity on the right-hand side of the inequality for the probability, oftentimes in literature, they'll call this thing delta. And you can think of delta as the probability of a bad event happening, i.e. in-sample error diverging from out-of-sample error by more than epsilon. And so if you call this thing delta, you can isolate epsilon using some algebra. So to get epsilon, of course, you're going to divide both sides of equality by 4 times the growth function of 2n, and then you're going to take the logarithm of both sides. That gives you this ln of 4mh2n delta, and of course e is to a minus power, so you're going to take the reciprocal of both sides. That gives you this e of uh, uh, sorry, the 1/8 epsilon squared n, and then you're going to multiply, divide both sides by n. That gives you this 1 over n. You multiply both sides by 8. That gives you the 8 over n. And then lastly, you take the square root, which gives you this radical. And this gives you an expression for epsilon, the error tolerance. And so with this epsilon, right, that epsilon is your error tolerance. And sometimes in literature, they refer to this as omega. And so essentially, when you talk about this probability delta of bad things happening, right, you can kind of flip or invert the logic here and talk about the probability of good things happening. What is the likelihood that E in and E out will be within some tolerance, right? And so that means with probability 1 minus delta, that's the probability that a good thing is going to happen, since delta is the probability of that bad thing happening. With probability 1 minus delta, at least, you're going to have a good thing happen. And what's that good thing happening? That E in is going to diverge from E out by at most this error tolerance epsilon. Because if the bad thing happening is that it's greater than epsilon, the good thing happening it will be that it's less than equal to what that epsilon is. And so we substitute in that expression for omega. And if you look at that expression for omega, it's a function of 3 different parameters that you have control over. Well, you don't really have control over the sample size. You can choose to sample more in a system, but nonetheless, it is a parameterized by n, the sample size, h, the choice of hypothesis set, and therefore the growth function in the VC bound, and also delta, the error tolerance. And so what does that mean? It says that if you want the same probability of good things happening and conversely bad things happening, if you want to change the hypothesis or change your sample size, this epsilon is going to change, right? So if you made n, the sample size, smaller, what happens? Well, if the sample size is smaller, well, this epsilon term is going to be bigger, so that means you have to relax your tolerance, right? Likewise, if your hypothesis set is more complex, what ends up happening is this expression for epsilon or omega is going to be bigger, and therefore you're going to have to relax your error tolerance. And so this gives us a way to look at the trade-offs that you make and whether or not you change something in your model, what the impact is, or that coupling, as it were, between the error tolerance and these different factors in your model. Okay. Any questions about this? Now, typically, because you have control over in-sample error, E in is typically going to be smaller than out-of-sample error, right? So if we take this expression, right, we say we can remove the absolute values, right, because E in is typically smaller than E out. And we take the same expression, we get E out minus E in is at most or less than equal to our omega. So using a little algebra, we add E in to both sides of this inequality, and we get a bound here on out-of-sample error. So our out-of-sample error is basically at most in-sample error plus some other criterion, right? And that other criterion involves the model complexity, H, as well as the number of samples. And so because you have control over the learning algorithm and over the hypothesis set, you can get E in to be closer to E out by reducing the model complexity. And if you think about it, if your model is less complex, going back to our expression for epsilon, that means for the MH, the growth function for VC bound, is going to be smaller, and that epsilon is also going to be smaller. But in this version of the expression, well, if your model complexity, if H is less complex, your hypothesis set, that means E in is going to be very close to E out, right? Because it's going to be E in plus some smaller quantity. And so this gets to something called regularization, right? Regularization is an approach that we will talk about in detail, for controlling the model complexity. Because at the end of the day, you want a good model, but you don't want your hypothesis set to be too descriptive, because we found if it's too descriptive, there's a very high probability that in-sample error is going to diverge from out-of-sample error by more than that tolerance epsilon. Okay. Any questions about this? Does that make sense? Okay. So that's what I had to finish up that module on the VC bound, and we'll pick right up with another module concerning an alternate characterization of learning feasibility. And this is based on something called the bias variance decomposition. And for this, we'll use an example that uses the squared error loss. Okay, so for reading. Now, we talked about generalization theory, and there's sort of three different ways to look at it. We talked about the growth function, that's section 2.1 to 2.1.2 in the book. Then VC dimension, which is 2.1.3 to 2.2.3. And then this last part, the bias variance decomposition, is covered in sections 2.2.4 through 2.3.2 in the book. And so all of these together comprise what we're covering as it pertains to generalization theory, which is a characterization of the expressiveness, as it were, of your learning model. And more correctly, whether or not your model is going to generalize well out of sample, and what the right context conditions are for that to occur. Okay. So let's, well, we just covered that, so I'm not going to repeat that because it's weird to, talk about the same thing a minute apart. And so I'm just going to skip over that, and let's jump right in to the bias variance decomposition. So essentially, you want to have your out of sample error to be small. That's really what you're after. And you don't have any control over out of sample error, right? But what you do have control over is in sample error. You minimize in sample error, and the hopes is that if you choose the context right, the complexity of your hypothesis set, and you search through it the quote unquote right way, and you have enough in sample points, that E out is not going to be very far away from E in, right? They're going to follow one another. And so we have a good approximation of F, we hope, and we want to perform out of sample, because if we can get a very good final best hypothesis that very closely mimics the assignment of +1 and -1 labels to new inputs out of sample, then yes, our model performs very well on data that it has not yet seen. And that's our goal. So we want En essentially to be a good approximation of F. And the hope is that in making En a good approximation of F, namely our final best hypothesis G, then it's going to generalize well. But there's a problem here. And as we saw with the VC bound, and we saw with this omega, that expression for omega, if you have a very sophisticated hypothesis set, that means you have many more degrees of freedom or parameters associated with the functions that collectively form your hypothesis set H. And of course, if the VC dimension for H is bigger, it's not going to perform well. That means En is going to diverge, or more likely to diverge, from E out. And so if we have a good, very sophisticated hypothesis set, it's very possible that your En is going to be close to zero, because a very descriptive hypothesis is able to describe many more ways of labeling +1, -1 on these in-sample points. But the bad news is that if it's too complex, it's not going to generalize well out of sample. And so the problem stems from the fact that you only know about your ground truth target function through the samples that it gives you. And therefore, you use these samples, iterating effectively through the different dichotomies. You use those samples in sample points as the way you test or try different candidate hypotheses drawn from this hypothesis set H. And so the problem is really one of how you identify a quote unquote good hypothesis, because you only can change the hypothesis you consider based on the data that you have, the in-sample points. And so you have to navigate through the space of all these hypotheses, little h, drawn from our hypothesis set, big H. and you do that using your data set. You can't actually see the hypotheses per se. All you can do is just look at how the hypotheses result on the labelings associated with the in-sample points. So if you have a less complex hypothesis set H, we just saw from the VC bound, that means you have a better chance of performing well out of sample or generalizing. Now, of course, how do you balance this? What do you do? And we're going to talk about an alternate way of characterizing this trade-off between descriptiveness and generalization out of sample, this tracking, if you will, or close tracking of E in to E out. We're going to characterize that alternatively using this bias variance decomposition. So what is the best type of hypothesis set you can get? Well, it's a hypothesis set that's very, very small, and that hypothesis set um, precisely describes the way the target function assigns these ground truth, these +1, -1 labels to the input points. And so, of course, such a hypothesis set would be singleton. Its set size only has a single hypothesis, and that hypothesis just happens to be precisely the ground truth target function. Now, that's a theoretical idea. That never happens. I have a hypothesis set that consists of a function 3x squared plus 17x plus 5.4, right? And that's absolutely perfect. That's exactly what the target function looks like. That never happens, right? But theoretically, the best hypothesis set you can have is one that's very, very small, only has a single function in it, and that function happens to be exactly the target function, right? So certainly this is laughable. It never happens. But that's the best you can do given the criteria at hand. And so essentially, using the probabilistic bound, what did we do using the VC bound in VC analysis? So VC analysis looked at the probabilistic bound on the situation or the events where in-sample error diverged, unreasonably so, diverged from out-of-sample error, right? And so this idea of a closest measure, and moreover, it said, what is the likelihood or probability associated when this closeless measure, this tolerance, is violated? And so through this analysis, we had this expression, and it said the out-of-sample error is no more than the in-sample error plus this other governing criterion we're calling omega. And omega is parameterized by the sample size, by the error tolerance, and also by the complexity of the hypothesis set. And so there's another decomposition that is sort of not competing, but it's just an alternate way of looking at things versus the bias variance decomposition, versus the VC bound, and it's called the bias variance analysis. And essentially what bias variance decomposition achieves to do is to directly model and therefore decompose the contributing factors that lead to out-of-sample error. And so the two things that bias variance decomposition considers when it's trying to describe out-of-sample error is how well the hypothesis set approximate the target function, right? How descriptive is it? Can it twist and turn and assign +1s and -1s in exactly the same way that the unknown ground truth target function can? And the other part is how well we can approach or identify a good H. That involves the way you search through the space of hypotheses. Because after all, when you're running your learning algorithm on your set of in-sample points, it's that learning algorithm's ability to try different assignments of +1 and -1, searching for that one that most closely matches the ground truth target function. So the methodology you use in how you approach or search for some through a set of small h's drawn from your hypothesis set is very, very important. And so to do this, it's going to use real valued targets. So it's going to be using squared error loss because it's mathematically convenient for simplifying the analysis. Okay, so let's jump in to this bias variance decomposition. So when we think of our learning algorithm, we said the learning algorithm halts, and when it halts, it outputs a final best hypothesis G. And the hope is that this final best hypothesis G will very closely mimic the ground truth target function. Now, this final best hypothesis G is going to be different depending on the specific instance of a data set you have. If you draw from that probability distribution that you don't have control over, you draw some sample of size n for your in-sample points, that's going to lead to a different final best hypothesis G if you have a different version of that data set. If you change the features, you're going to change the ground truth, the final best hypothesis that your algorithm halts on and outputs. Does that make sense? And so notationally here and in the book, when they write the final best hypothesis G in this decomposition or this expression of out of sample error, they parameterize it with this superscript script D, right? Because it's a different G that you're going to get for one version of a feature of a data set versus another version of a data set. Does that make sense? Okay. All right. So now we have G. We also have F, our ground truth target function, right? So F is out there, it's unknown. And in this case, remember again, for this decomposition, we're going to use squared error loss as a way of measuring the coincidence between the label assigned by the ground truth target function and the final best hypothesis. It's still called a label because it's a number, but in this case, instead of being +1 or -1 binary labels, it's going to be an arbitrary real value. Okay? All right. So if we look at the squared error difference between our final best hypothesis for a given data set script D and our ground truth target function, we can evaluate that on a single input, a single feature vector from our set of in-sample points. And so we evaluate G superscript D on X, and we take the squared difference between G on X and our ground truth target function F of X. Okay? Now, of course, because we have a data set, all data sets, as we said in our anatomy of a learner, are the feature values you get are determined by a probability distribution, right? You don't have control over it, but it's still out there giving you the actual feature values associated with each d-dimensional vector valued input x. And so if we wanted to know out of sample what our out of sample error is, we need the expectation because we want the probabilistic average difference between our final best hypothesis, which differs based on the choice of data set, and our ground truth target function. And so we take this expectation with respect to x, and in this notation, expectation with respect to x, the probability we're going to use in that expression is P of x, the probability that governs the feature vector values that you see for a particular data set. Does that make sense? Okay, so that's going to be our out of sample error. Now, of course, we have this free parameter script D. What are we going to do with that script D? Well, we just said that script D is a data set, and if you have one version of a data set, you can certainly have another version of a data set. And so each possible data set, and this is a theoretical construct, you can think of a probability, and that probability is going to be over a very large support set, right? But a particular instantiation of a data set is going to be associated with a probability. So you have some probability giving you, let's say you have n data points, right? One particular choice of n data points is going to be different from another particular choice of n data points. So certainly there's some probability that you can use to describe all of those different data sets of size n that you can be given, right? And so what we're going to do is we take this expression for out of sample error, and now we're going to envelop that inside of another expectation, because not only do you want the expectation of this squared error loss between our final best hypothesis G and our target function with respect to the x vectors, we want to have that expectation, take the expectation of that expression with respect to all possible data sets that you could have. Does that make sense? Any questions about this? Okay. So if I take the expectation of E out of G script D, that's just going to be the expectation with respect to the data set of the expectation with respect to the X vector values of the squared error loss between our final best hypothesis for a given data set evaluated on each point X, and its loss between X, between the final best hypothesis on X and the ground truth target function on X. Okay? All right, so mathematically, we have an expectation. Now, expectation for a discrete distribution is just the sum, and you're taking some quantity and you're multiplying it by a probability. If you have a continuous distribution, it's an integral, and you have some quantity multiplied by its probability. Now, of course, you have two expressions. In the original expression, you have the expectation with respect to D and expectation with respect to X. Now, of course, you can reverse these two. And the reason why you can reverse them is because you can apply a different integral, either the integral with respect to the probability distribution for x or the integral with respect to the probability distribution over the data set, right? And so it doesn't matter which one you do first, and mathematically, we can switch this outer expectation with the inner expectation. Does that make sense? And it's the same exact expression. Okay, so let's do that. And what we're going to do is focus on this inner expectation with respect to the data set. And then later on, when we get that result, we're going to apply that result to the outer expectation to complete our solution for out of sample error. Does that make sense? Okay, so let's first consider this inner expectation with respect to data sets. Okay, so we're going to introduce some other notation. And this other notation is going to talk about this concept of an average final best hypothesis. Every time you get an instance of a data set, what happens? Let's consider a data set of size n. So you get some feature vectors, x, you have n many of them, and you run your algorithm halts, it outputs a final best hypothesis g. You get another data set that's different from the first one. It's n data points. You run your algorithm, it halts, and you get a final best hypothesis G that's a little bit different. Now, each of those final best hypotheses, well, if they produce the same labeling as the other final best hypothesis, well, it's going to be the same, but if it's a little bit different, now you need to make a choice. How do you represent, out of all the possible final best hypotheses you can have, one on each of the different data set choices you can have, how do you represent this idea of the global overall best one? And so that's what this G bar is. This G bar is the average final best hypothesis. You can imagine if you have, let's just for the sake of considerations, let's say you had 1,000 different data sets, right, of size n. So for each of these 1,000 data sets of size n, you're going to run your learning algorithm, and it's going to halt for each of these 1,000 data sets of size n, and it's going to output a final best hypothesis. So what do? Well, you evaluate each of these final best hypotheses on your input x, and then you take the average output, right? That's one way of calculating your G bar. And G bar is the average final best hypothesis, and this is the best you can do not knowing anything else about the problem, right? It's the average output that your final best hypothesis will output, and we take the average because this final best hypothesis will be different if you input different data sets and run your learning algorithm. Does that make sense? Any questions about this? Okay. So we have this G bar, and literally, given different data sets, in this example, k many data sets, you would literally run your learning algorithm, and then when you get your final best hypothesis on the first data set, the second one, the third one, up to the kth, you add together all of those outputs for the final best hypotheses, and then you take the average. That's literally what G bar is. Okay. Any questions about this? Okay. So let's continue on, and let's go back to the original expression that we had. We had the expectation with respect to the data set of our final best hypothesis indexed by the data set, evaluated on x, and we had the square error loss between that final best hypothesis and the ground truth target function. And we took the expectation with respect to the data sets. Okay, so let's do a little bit of manipulation. And certainly this expression that's parenthesized where we're squaring, we can add 0 to that parenthesized expression. It doesn't change the value. Okay, well, one way of adding 0 is to add G bar and subtract G bar, right? It doesn't change the value. So now that we add G bar and subtract G bar, I'm going to group together the first two terms, G superscript script D of x minus G bar of x, and I'm going to group together the third and the fourth term, G bar of x minus f of x. That has not changed the value of the expression. All I've done is associated the first two terms and the second two terms in their addition and subtraction. Does that make sense? Okay, so now I'm going to compute the square, right? I have two terms. One term is g of x minus g bar of x. in parentheses. The other term is g bar of x minus f of x. So if I square that whole thing and I have two terms, let's refer back to what it is to multiply terms for a polynomial. Let's say if I have a plus b times c plus d. And it doesn't matter if it's plus or minus. Minus is the same as adding a negative number. So what do we do? Well, first we multiply the first two terms. That's ac. We multiply the last two terms. That's bd. And then we have the cross terms, right? The cross terms are bc and ad, right? And so we're going to do the same thing. We have two terms. We have g of x minus g bar. So we're going to, if you multiply, you're multiplying by yourself. So let me do that example on the board. If I say a plus b to multiply by itself times a plus b, well, that's a squared, the first term squared, a squared, plus the second term squared, b squared, plus b squared, plus 2 times the cross terms, plus 2ab, right? So I'm going to do the same exact thing, only instead of saying ab, I'm going to say g of x script d minus g bar of x for my a term, and my b term is just a parenthesized expression as well. Does that make sense? Okay, so if I do that, okay, what do I have? I have the first term squared, right? That's g script d of x minus g bar of x squared, okay. I have the second term squared, that's g bar of x minus f of x quantity squared, plus 2 times the cross term. The cross term, 2 times g of x minus g bar times g bar of x minus f of x. Okay, so that's what I get, and it's just applying the FOIL rule, or if you want to call it the square and cross term rule. I'm just applying that simple rule for multiplying out polynomials to this expression. Okay, so now I'm going to look at that expectation. Now in this expectation, I'm going to make an observation. This is an expectation with respect to d, right? And so in this observation, I notice that I have some terms that don't involve that d, right? And so if I have an expression under an expectation that does not involve the variable of interest under that integral, that for all intents and purposes is a constant, right? And so the expectation of a constant is just itself. So this term, that g bar x minus f of x, that's going to come out, right? Because the expectation of a constant, and this is a constant because it does not involve script d, the data set, that variable of interest for the expectation. So that's just going to come out on its own, okay? Now if I look at the second term is interesting because in the second term here, I have something that involves d times something that does not involve d. So that term that does not involve d, that looks like a constant. So it's like saying a constant times a variable as far as that expectation is concerned, right? So that's going to be this g bar minus f of x times something under an expectation, right? So I have 2 g bar minus f of x times the expectation with respect to d of this term, the g script d of x minus g bar of x. Does that make sense? Okay. So if I do that and I apply this expectation with respect to d for that first factor multiplying by the 2 here, what do I get? Well, this g bar of x, that looks like a constant, right? But this term here, the g script d of x, well, wait a minute. That g script d of x, if I take the expectation with respect to d of this g script d of x, let's see what we get. And so for that term, we say the expectation with respect to d of g script d of x, right, minus g bar of x. Well, what is that? Well, this part comes out the g bar of x because it does not involve script d. So that's the same as the expectation of d of g script d of x minus g bar of x, where the g bar of x is not under the expectation because that's a constant. Now, the expectation of g of x script d, well, that's just g bar, right? That's what we started with. If we go back one slide, g bar is the average best hypothesis. And that's exactly the expectation with respect to the data set, script d, of g script d of x, okay? And so essentially what happens here, this term under the expectation with respect to d, well, you're going to get a g bar of x minus g bar of x. So you have a 2 times g bar of x minus g bar of x times that g bar of x minus f of x. So that's going to be 0 for this first parenthesized expression, right, on that third line. And 0 times anything is always 0, right? So the end effect is this third term goes away, goes to 0, right? It doesn't matter. This first term, we have the expectation of g script d with respect to x minus g bar of x, quantity squared, plus, well, this is a constant, so that second squared parenthesized expression, it comes out because the expectation of a constant is just that constant. Does that make sense? Any questions about this? Okay, so this is the expression we get, and we get the expectation with respect to d of the difference between the final best hypothesis you get from a particular data set, quantity squared, the loss, squared error loss between that final best hypothesis and your ground truth target function, is the expectation of that final best hypothesis minus the difference between that and the average best hypothesis, the squared difference, plus the difference between the average best hypothesis, final best hypothesis, and our ground truth target function. Okay, so this is what we get after doing a little bit of algebra. And essentially, what this gives us is on the right-hand side of equality, that first term describes how far your hypothesis is from a particular data set. This is the best you can get for any data set, right? So let me explain what I mean by that. So G bar is the average best hypothesis. It's the best you can do for any data set, right? You notice G bar does not have any sort of script or index with a data set. G bar is the absolute best you can do. Now you notice here G of X, that's indexed by a data set. So your G is going to change. And what this G changes with is your data set. So essentially that first term says, on average, as I change the data set, how well does your best hypothesis do relative to the absolute best I can do, which is G bar. Does that make sense? Okay, so if you change your data set, your hypothesis is going to vary. Okay, now the second term here, G bar of x minus f of x quantity squared, this is the distance from between the best hypothesis you can ever get on average, G bar, and your ground truth target function, right? Okay, so these two quantities together are going to tell you about your out of sample error and how well your learner can perform. And so these two things have a name, right? The second term is called the bias, and the bias represents how limited or how descriptive your target, your hypothesis set is in trying to match the way your ground truth target function can assign +1, -1 labels, or not +1, -1, can assign labels, because here we're talking about real values. And so this bias talks about the descriptiveness of your hypothesis set relative to the ground truth target function, right? Now this first term on the right-hand side of equality talks about the variance. Now this variance represents the way you search for the best hypothesis, because the way you search for different data sets, even for the same data set, if you initialize your search from different locations, the way you search is going to result in a different final best hypothesis. And we saw that on the assignment. When you randomly initialized PLA, it was different from you initialized it with a regression bootstrap, and it was different from when you searched using a learning rate versus just doing the full update. And so this variance talks about from one data set to another, how different will your final best hypothesis be relative to the best you can do, G bar. Okay? So we have these two components. we have the variance term and we have the bias term, which together decompose our out of sample error. Okay, but we're not done yet, right? Because here you'll notice for the bias and the variance, everything on the right-hand side of equality, we have a free parameter. Likewise, on the left-hand side of equality, we have a free parameter. We've captured the d because we're taking our expectation with respect to d, but we have here a free variable, our x, right? So remember, we said we're going to evaluate the expectation with respect to d, and then later, after we solve this, we're going to use that expectation with respect to x because we started out reversing the expectations, right? The ordering of these expectations. So let's do that. So now we're going to complete this by taking our expression, the bias variance, on a single point, and we're going to apply now this expectation that we had saved for later with respect to x, and we're going to take the expectation with respect to x of this bias term on x and this variance term on x. And so that gives us our result, and that result is the bias, the total bias, and the total variance. Okay. Any questions about this? Does that make sense? All right. So what does bias and variance look like? So let's have some kind of more visual examples. So in the left-hand frame, we have our expression for bias, and we said that bias is a measurement of the descriptive power of your hypothesis set. And we said G bar is the average final best hypothesis. So let's take, for example, this relatively small hypothesis set. Now, if you were to take the average of all the hypotheses, you can think of the hypothesis as being a weight vector associated with each dot that we have drawn in this fictitious hypothesis set. If you were to take G bar, the average best hypothesis, we call it this dot here right in the middle, right? Now, there might be other hypotheses that are better, closer to our ground truth target function. There might be some that are worse, but you don't necessarily have control. I mean, yes, you have control over the algorithm with searches, but you might not have enough data to exhaustively search the space of all possible hypotheses, right? So G bar is the best overall that we can do, irrespective of the type of data that we have or the choice of data set, right? So this distance between our our average final best hypothesis G bar and this ground truth target function, that's called our bias, right? And it says how descriptive relative to the ground truth target function is the best that you can do in any case of a data set or a feature vector. Does that make sense? And so if this hypothesis set is very, very small, what ends up happening is that the bias goes up, right? If it's very small. Now, let's take the case of having a very large hypothesis set. That would be like saying the set of, degree 1,000 polynomials. You can describe a lot of things with a degree 1,000 polynomial. But the problem is maybe that hypothesis set is so big that it includes the ground truth target function. That's wonderful. And you might think that's a big win, but the problem is it's too big, right? And so here in this very large hypothesis set, because it does include or envelop the ground truth target function, but the problem is it's so big that you have a lot of choices for what your ground truth, for what your target, what your hypothesis could be, right? So when you initialize your search, regardless of how you initialize it, your final best hypothesis, there are many different choices for what that final best hypothesis G could be. Some cases you might not be lucky enough. Your G might be somewhere over here, or your final best hypothesis might be somewhere over there. Now here we have this red cloud drawn from your space of functions, your hypotheses, and that red cloud represents all of the possible halting conditions for which your algorithm has output a final best hypothesis G. Now, if you look at the size of this red cloud here, that's called your variance. So that says for some learning algorithm or choices of learning algorithms and a very large hypothesis set, if you initialize it differently, and you'll actually see this, you'd see this play out in MATLAB if you tried it on one of the assignments. If you initialize it differently and let your algorithm halt, you're going to get different choices of final best hypothesis. Likewise, if you took some of the feature vectors from your in-sample points and you changed them a little bit, you're going to see your final best hypothesis when your algorithm halts. You're going to see it change. And so this red cloud represents all of the different choices of final best hypothesis you can have. And that's called the variance. So the larger the hypothesis set, the larger the variance is. But you'll notice here, if you have a big hypothesis set, the bias is going to go down because this distance between the hypothesis set and the ground truth target function is going to be smaller because it has such a broad representation. It's going to get closer and closer on average to the ground truth target function. But the problem is, from one instance of your algorithm, your model, to the next, it's going to jump all over the place. And so it's going to have higher variance in what this final best hypothesis could be. Now, the problem with this is you don't have an infinite amount of time in which to run different versions of your algorithm to find the best of the final best hypotheses. You have your data set, you run it once, and you really don't know if, given a large variance, if you're going to get closer to the target or you're going to be further away from the target. So that's the particularly damning thing about having a very large hypothesis set. Well, that hypothesis set might be descriptive enough to perfectly coincide theoretically with the ground truth target function, you might not be able to find that right final best hypothesis to give you good results. Okay? And so in general, if your hypothesis set is big, your bias goes down, but your variance goes up. If your hypothesis set is small, your bias increases, but your variance goes down. So which between the two extremes do you choose? That's a good question. It depends on your problem. Right? And so this is one of those natural tensions between two competing factors in a learner, is the trade-off between bias and variance. Now, there's a framework called regularization that we will talk about, which is a mechanized way of encouraging simpler hypothesis sets. And that's added as a penalty term, if you will, to the loss function. And I'll talk about that when the time is appropriate. But at this juncture, we have this trade-off between bias and variance. And when you look at the quality of a learner, you evaluate the bias and the variance, and it's the sum of these two quantities, whichever is the smallest, is the best out-of-sample performance. Okay? All right. Any questions about this? No? Okay. So let's take a look at this example. I'm going to do a time check, 5:16. In this example, we have a sinusoid. And the sinusoid is a real valued target function. Now, all throughout the semester so far, we've been saying that the ground truth target function is hidden from you. It is, right? But in this case, we're going to show you what it is. F of x is equal to sine pi x, because we need to be able to validate that the theory holds true, right? So for this example, you see the ground truth target function, but in actuality, you only see the samples that the target function is labeling. Now, this target function, it runs from -1 to +1. So the sinusoid is evaluated between minus pi and plus pi for a total of 2 pi domain for the sine, right? But the function itself is going to go in input for x goes from -1 to +1, okay? And now the samples, we're going to have a very small sample size. N is going to be 2, so we're only going to sample 2 points from this sine wave. And it doesn't matter where these points are drawn from, but nonetheless, we're going to have 2 points that we draw from it. And you're only, as a model, going to have access to the 2 samples. And now we're going to have 2 hypothesis sets. The hypothesis set, which is the constant hypothesis, so h of x is equal to b. It's just going to be a straight line horizontally going across. And then we also have a more complex hypothesis set, h1, and that's going to be a line. H of x is equal to ax plus b, a slope and a y-intercept. And so the question we're asking, and we're going to use the bias variance decomposition to answer this question, which hypothesis is better, h0 or h1? Now you might think, gosh, this is a sine wave. So if you have any 2 points along the sine wave, you might think, gosh, well, maybe the straight line is different because a straight line can kind of tilt to try to accommodate regions of the sine wave. but it's not that intuitive, and we're purely going to use the bias variance decomposition in order to determine which one of these two hypothesis sets is different. Now, clearly, the H0, it's more simple. It only has one parameter, B. H1 is more complex, it's more sophisticated. It has two parameters, A and B, governing it. So the parameter count is different for H1 versus H0. And moreover, H1 is more descriptive than H0. H0 can only go straight across at a different height. H0 can only go straight across at a different height, but H1 can tilt arbitrarily. Okay? All right, any questions about this? No? All right. So let's try to do an approximation. This is just a straight mean squared error approximation with a constant line from H0 to try to best fit the sine wave. And we're going to do the same thing with a sloping line to try to best fit the sine wave. Now this is just, you could do something in MATLAB, do a mean squared error fit, and what you're going to get for H0 is going to be a line, horizontal line that passes through 0. So h of x equals 0. And if you wanted to compute the out-of-sample error for that best fit associated with H0 hypothesis set, it's going to be this area. And you can actually numerically calculate that. And if you did, out-of-sample error is going to be 0.5. Okay. If you do the same thing, a mean squared error fit from the set of lines to the sine wave, and you can actually take points along the sine wave and take a line and do a mean squared error fit, and you're going to come up with that line, right? And in similar fashion, if you take the area of the difference between our best fit line from H1 and the sine wave, your out of sample error, which is what that represents, is going to be 0.2. Okay, does that make sense? All right, so we're going to do the bias variance decomposition numerically using something that looks like learning, and will show that our numbers for E out and E in for E in gets very close to these numbers that we see here for out of sample for both of these. All right, but we're going to use it to choose which is the quote unquote best hypothesis for this particular example. And mind you, for the learning problem, we're only going to use two samples drawn uniform at random from the sinusoid. Okay, so what happens in learning? So we take our sine wave, and in the H naught, bless you, in the H naught case, we're going to sample 2 points arbitrarily from the sine wave. And so let's say we sample these 2 points from the sine wave. And now what we're going to do is we're going to learn them from a line, a constant line drawn from H naught. Now, what line do we choose? We choose the line passes through the midpoint of the y values associated with the samples from that sine wave. And that's going to be the best fit line for those 2 points, right? That's what happens in learning. You're taking your in-sample points and you're trying to produce the same values that mimic the ground truth target function, but you're only using functions drawn from that H naught, okay? And so it's trying to produce that value for the first point and for the second point. The best it can do is sit there right in the middle, okay? So likewise, we're going to draw those same 2 points, right? And those same 2 points are going to be used with hypothesis set H1 to try to learn the labeling. Now, of course, using the point slope formula, you can find the line that mimics as much as possible that y value associated with each one of these points, the sinusoid's output, ground truth target function. And this is the following straight line, right? It passes through both those points. So yeah, it's predictive. It gets the same value it returns for the first point, the same value for the second point. Wow. Our in-sample error seems like it's 0, right? Here, our in-sample error for H0, it's a larger in-sample error, right? So let's continue forward. Does this make sense? Okay. So what we're going to do is for H naught, we're going to repeat some number of times, a large number of times, sample 2 points from the sinusoid, and then we're going to do the best fit line from H naught, right? And so sometimes you're going to sample points that are like here and here. Sometimes you're going to sample points that are here and here. So you're going to get a lot of different lines from H naught that best fits the 2 sample points depending on the value of those 2 sample points. And just going to repeat that again and again and again some large number of times. Okay? And likewise, we're going to do the same thing with H1. If you get 2 sample points, say here and here, right, you're going to get something that looks like a 45-degree slanted line. And if you look at the sinusoid between what looks like pi and 1.5 pi, right, for this wedge that's 180 degrees represented, pi radians, you have a lot more regions of the sinusoid in that area. And so you're more likely going to select points that are in this area. And you'll notice here there are not more lines in that area towards the center. But nonetheless, for every 2 points you sample from the sinusoid, you're going to fit the best fit line drawn from H0 because it's trying to mimic the real valued output associated with the ground truth target function, namely the sinusoid. Does that make sense? Okay, so now what we're going to do, for each of these, we're going to compute the average final best hypothesis. And so for every choice of 2 data points, you're going to get a different G. And what we're going to do is literally take each one of those G's and take the average. And that's going to be our G bar. So if we do that for H naught using this experiment, this is our G bar, the green line, in the upper right-hand frame. And that's G bar. And guess what? That's exactly the best fit from before when we're just using least squared error fit. Likewise, if we take the region spanned by all the possible values of G as we go from one round to the next, a different data set to another version of the data set of size 2, we essentially take the standard deviation of that region, and that gives us this gray shaded region, right? That's our variance, right? And so that standard deviation, which is square root of the variance, it talks about the dispersion of all the different solutions we can get for final best hypothesis from one version of this data set of size 2 to the next one, to the next one, to the next one. Does that make sense? Okay, so likewise for H1, we do the same type of analysis. For all of the different values of our final best hypothesis G, we're going to take the average, and this gives us a G bar, and that's this red line, right? And that G bar looks a lot like the least square error fit, the best fit. It almost precisely coincides with what we did numerically at the outset. And then we also take the standard deviation spanned by all the locations of this G bar, this line, and this gives us this gray region, and that's our variance for hypothesis set H1. Does that make sense? Okay, so we have the G bar for both H0 and H1, and we have the variance for H0 and H1. So now what we're going to do is we're going to compute the bias and the variance. We're basically going to add up these areas and then add together the bias and add together the variance. And so the bias is a measure of difference between the ground truth, blue, sinusoid, and the G bar, that's our bias. In the first case, our bias is 0.5. That's exactly what out-of-sample error was when we did the numerical approach. The variance, we're going to add up the area for this gray region, the variance for H naught. That variance is 0.25. Okay. We do the same thing for our solutions for H1. We're going to compute the bias here for our G bar, the difference between G bar and our ground truth target function, sine x or f of x. That's 0.21. From before, when we had the numerical solution, our out-of-sample error was 0.2, right? So 0.21 is pretty close, but nonetheless, their bias is 0.2. And then this gray region associated with H1, you notice the variance is much higher, right? It's 1.69. So if you're given a data set of size 2, right, and you run this experiment and you want to know the out of decomposition for the out of sample error because you want to have the smallest out of sample error, that's the best performing model. Well, if you add the bias and variance for H naught, it's 0.75. If you add the bias and variance for H1, that's 1.9, right? So that means H naught is the better hypothesis set. Does that make sense? Okay, so that's what the bias variance decomposition does. And we have this simplified example, be it a naive example, because in this case, you're being shown what the ground truth target function is, right? But in truth, when you're doing this for real, right, you don't have access to the ground truth target function, but the bias variance still applies, okay? All right. So what does this say? Well, we had a data set of size 2, and that data set of size 2 is very simple. We had a more descriptive hypothesis set H1, and we found that H0 that had one parameter was a better choice than H1 that had two parameters. And what this says is when you have a choice of models of hypothesis sets to use in your model, you match the model complexity to the data resources that you have, right? Not to the target complexity. And essentially, we saw this with the VC bound, right? We said the growth function has to be polynomial in order for that decaying exponential in n to be able to for a suitably sized data set, to decay it so that that probability of bad things happening is really, really small, that bad things happening is a rare event. Said differently here, you want to make sure that you make your model only as complex as you can afford in terms of the data resources. If you have a lot of data, you can afford a more complex model. If you only have a little data, your best choice is to have a less complex model. And we saw that here with a data resource of size 2, our data set. Now, naively, you might think, gosh, use the more complex model. But you'll notice where we really went wrong here, yes, so the complex model, the bias is smaller. As the hypothesis set gets bigger, the bias is smaller, right? But where we really lost out here with this more complex model is in the variance. Because it's so big, that solution can vary very widely, and you really need to get very lucky to select a good one. So on average, you're better off selecting the simpler model. And so that says that if you want to build a learner that minimizes out of sample error, i.e. generalizes well, choose a model only as complex as you have the amount of data to pay for that complexity, right? And so what you learn depends on the data that you're given, and you don't have control over that data. So the question is not, is the target function there? Yes, the target function is there. With a huge hypothesis set, you could theoretically find the target function, right? You could find it precisely, but you're never going to find it if you don't have a lot of data because you can't explore different dichotomies, as many dichotomies. And so the question is not, is the target function there? It's, can I find the target function given the data resources that I have? And if you can't, then you need the simpler hypothesis set. So you have to pick a hypothesis set that you can, quote unquote, afford to navigate given the data resources at hand. Does that make sense? And when I say given the data resources you have, when we talked about dichotomies to kind of relate bias variance back to VC bound, is that you explore the space of hypotheses by essentially, when you generate a new hypothesis that you consider, you're trying a new dichotomy, right? Because if you do the PLA update, it's going to correct one of those misclassified labels, changing the dichotomy. Something that used to be +1 is now going to be -1, or something that was -1 is now going to be +1. And so essentially, when you pick a hypothesis set, you're going to pick one that you can afford to afford in terms of the data resources. So you match the complexity of the model to the data resources, not on the target complexity that you think will best mimic the ground truth target function. Does that make sense? And so one of the laws of machine learning is you have to pay for it, right? And how you pay for complexity is with data. If you have a certain amount of data, you don't choose complexity that you can't afford, right? Or else E in and E out will diverge wildly. And we saw with bias variance how that plays out here, as illustrated for H1, is with a much larger variance, and that's what loses out when you add the bias and variance components of this decomposition. Does that make sense? Okay, any questions about this? Okay, so if there are no questions, I think that was it, and I will end there. Let me check the time. It's 5:32, and I will see you all on Tuesday.